Sorry for the interruption. This means a 10 kilowatt hour energy draw times the 13.4 cents per kilowatt hour means this would be $1.34. What would draw 10 kilowatt hours in your house? Well, that's 10,000 watts. Your hairdryer can be up to 2,000. This would be the equivalent of 5 hair dryers on full blast for an hour would only cost you $1.34. Electricity, contrary to the public's belief, is incredibly cheap. Now, in the physics class, we're not interested in cost, only in joules. So if you want to convert this straight to joules, just do what I showed you. Take the K, throw on 3 zeros, take the hours, change it to 3,600. You've got your conversion done. It's so easy, it's not worth memorizing. You just got to think about what it is you're doing. The next part would be solar power. This is another energy source that we can't count the energy without dealing with the time. So it's easier to talk about the power. The sun's output continues. It never stops. So just like rain, you can't talk about a total, only a rate and the duration. When measuring rain, of course, the bucket diameter is part of the equation. A bucket twice as wide will catch 4 times more rain. Imagine 2 buckets, radius r and 2r. So the formulas are this, pi r squared and pi 2r squared. We expand this, we get pi 4r squared. The only difference between these two areas is that number 4. Pi r squared, 4 pi r squared. Twice as big bucket collects 4 times as much rain. So instead of just talking about the wattage of light raining down on us, we talk about the wattage or energy flow rate divided by the bucket that's being caught in. So we tend to talk about sunlight and other forms of radiation as power in a unit area. At the top of the Earth's atmosphere, the sun emits 1,400 joules per second onto a surface area of 1 square meter. It's a very simple concept. Talking about the total energy of the sun means nothing. The sun is delivering 1,400 joules per second on this patch of ground every second for eternity. So you need to talk about power times time to get your energy. That was not needed in the other physics where the height of an object is mgh. You get a total energy by lifting something because you lift it from one state to another. It's not a continuous change. Let's say you have 1,001 watts of sunlight for 1 hour. What's the energy? You just multiply the watts of sunlight exactly like before. Now, if I say it's 1,000 watts of sunlight per square meter, then you'd say I got 3.6 million joules in a square meter. That's the only difference between an intensity calculation and a straight up power to energy. In practice, as sunlight rains down on things, we don't catch it all. So what is termed the irradiance or insolation is the light that reaches an object. And it's at best on the surface of the Earth 1,000 watts per square meter. That's on the equator on a cloudless day. So that's the number we're going to work with. Canada is a lot further north than the equator, so this number probably drops to like somewhere between 600 and 700, 750, because our country also spans a huge north-south distance. And this value is going to be ridiculously weather dependent, okay? The cells themselves are typically 10 to 15% efficient. They are getting better by quite a bit as time goes on, like significantly better. Some of them have doubled their efficiency over time. But when you take one cell and you wire it up to a panel, you lose some efficiency as well. So in any readings you do, there are cell efficiency and panel efficiency. This is how well the cells have been improving on. Some of the top ones have almost hit 50% efficiency, but these are out of reach of the average person. This would be about as best you could do, realistically. But that's not bad. It's still, compared to computers are like 1 billion times more powerful than they were in the 50s. The solar cells have only kind of tripled it. This is pretty self-explanatory, why solar power works best at the equator. And you can actually calculate it quite accurately, but that's beyond this course. In practice, energy companies will put out these maps, and they will show you where you can best utilize solar power in the country. They have the weird units of kilowatt hours per kilowatt year. And what that means is, if you install a 1 kilowatt panel and let it run for a year, what is the total energy you might create? So in Ontario, let's round this number, we'll call it 1,000. If you put in a 1,000 watt solar panel in Ontario, by the end of the year, you might get 1 kilowatt hour of energy. Kilowatts and kilowatt hours are different. So these are based in practice. At best in Ontario, you might be able to get 1,200 kilowatt hours from a 1 kilowatt panel in a year. You can see the time of month. And obviously solar power up here, not very useful. 1,200 kilowatt hours can be turned to joules, but we don't need to here. At maximum, electricity costs in Ontario 0.13 kilowatt hours. At maximum. You take this cost and you multiply it by what your solar panel was able to provide, you could save $156 in a year. Is that very much? No, it's not, because my hydro bill goes from $50 a month to $400 over the course of the year. So I'm paying about $300 a month for hydro. A 1 kilowatt panel is going to cost you about $3,000. You spend $3,000 and you will save this much a year. It's going to take you about 20 years for the solar panel to pay for itself. And unfortunately, after 20 years, the panel itself may be dead, though it's getting better. But it is not this salvation that it's claimed to be. It's an expensive source of electricity, but it is getting better.